Function literals give you the ability to define functions on the fly and succinctly, which is very useful when we're working with these higher order functions like filter, map, and reduce. So to set the stage here, let's imagine we've got a list of strings A, AB, ABC, ABCD, and we're trying to filter these strings, so we want to find only the strings who have a length greater than 3. In this case, we can tell that there's only one, right? ABCD. So we would define a function that's a predicate, right? It's a predicate because it returns a Boolean and takes in a single value of some type. And those types match up with the list we're trying to process, right? We're trying to filter x's whose type is a list of string. So we need a predicate of type string, meaning its item parameter must be of type string. Right? And so first we would need to define our list, then we would define our predicate, and then we would define, or we would call the filter function using those two values. And so the question is, do we really need to define a brand new function and put a name on it every time we want to filter our data? What if we're just exploring our data? Wouldn't it be nice if we could just do this in a more succinct way without having to define a function separate from using filter? Right? And as some intuition for this, I think you can believe me when I say, well, we didn't actually need to define if a variable named x is. If I had filtered and I had called as a nested function call this listify function here, we could have substituted x's with this actual value that it was computed by. And what we're going to see with function literals is, well, if isLong is defined by what we're seeing here, right, this function syntax, then shouldn't we just be able to write that function syntax right here where we had written isLong, the name of the variable that held that function value before? So let's check it out and see if we can. It turns out we don't have to. We can simply write that same line we saw before. If we had a variable list named x's, a list of strings, we can filter it by writing a function literal, meaning we're literally writing a function definition as a parameter to this filter function. And I'm outlining it in pink, right? So notice we've got our parameter list, we've got our return type, and we're returning true when length is greater than 3, right? And so if we just wanted to play around with some data and filter some values more succinctly, we wouldn't need to go to the effort of defining a completely separate function. We can write a literal in this way, right? You'll see that these things are called anonymous functions because this is a function with no name, right? And in other languages, you'll see them called lambdas and closures. Just as a side note, the idea of a closure is this, but it involves some extra ideas that we're not going to get to in Comp 110. But closures are super cool, very powerful. If you're feeling adventurous, search around for them on the web. All right, so let's go actually try using this in some example code. So I'm going to switch over to today's materials, and I've changed my example to the O1 function literals app. And we've got some setup here that we can talk through. So we've got a list of string values, University of North Carolina. And when I print that input list, we see that we get an output in list form. And we're going to move through a series of steps to get some practice with function literals in this video. The first thing I want to point out is that if we scroll over and we see that we're importing some functions from this list algos file, there's a third file in this directory for today's lecture materials that contains definitions for the interfaces predicate used by filter, transform used by map, and reducer used by reduce. And then we have implementations of those functions down below, right? So these are the three implementations of those algorithms. We're importing those three algorithms into this example file. And then I've defined three functions down below. The first is a predicate, the second is a transform, and the third is a reducer, which we're going to work with as we move through these examples. So filtered, rather than assigning it the empty string, let's try filtering with our items, which is our input list. And the test function, the predicate that we're going to apply is long word, right? So we'll come back to this. And when I save this, notice that right now we are seeing only the words after we've assigned the result of that to filtered. The filtered values of this list are University of North Carolina, right? The word of was filtered out of the result because it didn't satisfy the predicate's criteria, right? It didn't satisfy the long word. So the idea that we're exploring in this video is, well, we didn't need to define this logic separate from our filtering, right? So I could have defined this function right here. So I'm going to say item is of type string, and its return type is Boolean. And if I give my function arrow, and then the body of the function is return item.length greater than 4, right? And I can now delete this function that was separately defined down below. And notice when I save, we get the same result. And we've defined our very first function literal here. Right? And so I'm going to make a note of filter using a function literal. Right? And so this is the definition of our parameters, our return type for this function literal, and then the implementation of that function, all written as a single parameter to this call to filter, right? So we're providing this this function defined inline as a function literal, all right? It turns out that if we define our functions in this way, TypeScript can be clever about how it infers those function literals parameters types and return types, right? So remember that the filter function is generally defined and generically defined as such. Right? We have filter is a function that's generic for any type t, where you give it an input list of node t, the test function of predicate t, and it returns to you a list of node t, right? So if we are trying to figure out what is the call to filter below, what do the types need to be for this function literal, right? So if I highlight the function literal here, we see this is the definition of a function literal. Well, considering this definition of filter, if the list here is node type t, this is going to be node type string, right? So that means that the second parameter here must be predicate of type string. And we know that based on the predicate functional interface that the item parameter must be of type string and the return type must be type Boolean, right? What makes something a predicate is that it returns to you true or false whether the next item that you're testing satisfies that predicate's logic, right? The test that it's performing. And so notice we didn't have to explicitly state those things here in this definition. We could fill in those blanks ourselves using some logic based on filtering a list of node type string, right? We were able to take what we knew from the first input parameter and say, okay, well, if this is going to be a valid predicate, then this item parameter must be type string and the return type must be Boolean, right? So it turns out TypeScript is able to make that inference as well, and we don't necessarily need to provide those values explicitly ourselves, right? So let's try rewriting our previous example using type inference, right? And then carry forward this example using a transform function and mapping, right? So what I'm claiming here is because we are filtering using an input type of node string, TypeScript is able to infer that this parameter type must be a string and the return type must be Boolean, right? And so notice that this became much more concise. And if we hover over a single parameter here, we see, sure enough, TypeScript knows that its type is string, and it's able to infer not only based on the body of this function, but also just on how this was used in the context of a filter call, that, hey, this has to be a predicate. That means it's going to return type, have a return type of Boolean. So let's try doing the same thing for a transform. So notice this transform function is just going to transform the first letter. So if we were to continue forward that process, we could imagine, okay, we're going to transform using the map function. So we're going to map our filtered list, and the transform function is going to be first letter, right? So we're going to map using the first letter, and if we take a look at what happens when we apply the first letter transform to each item in our input list, which was our filtered list, right? We take the first letter from university, the first letter from North, and the first letter from Carolina and make a new list out of those values. We see that we've transformed one list of strings into another list of strings. Well, let's try writing this with function literal syntax. Right? So instead of first letter, we could say, okay, the item is going to be of type string, and we know that because notice we know that we're defining a function that must satisfy the transform functional interface because we're using map, and it's going to return the item index 0, right? So the first letter or the first character of that string. And notice how concise that was. We can actually get rid of that first letter. I'm actually going to make some space between each of these steps so that this is a little bit clearer. And so we're mapping our filtered list, which was the result of the previous step in this process, using this predicate or this transform function that is defined as a function literal. And so given an item, and we can see that that's of type string, return something that's of type string. And now our transformed list, when I save this all just works out, right? And so notice how terse this is. We're saying map our some list, and here is the exact tiny little transform function I want you to use to make that happen, right? To make that mapping, and select only the first letter of or first character of each string, right? So it turns out in certain cases we can get even more terse than that, right? So let's take a look at what we just did with some additional notes. So again, higher order functions must specify the parameter type of what is expected, right? So a filter function requires a predicate function of type t, right? So that means that the predicate function that we pass in, the test function, has to satisfy this functional interface. Given an item parameter of type t, return a Boolean. And so when a function literal is used as a parameter, as we just saw, TypeScript can infer the parameter types and the return type of that literal. Right? We don't have to write those explicitly out because it's embedded in the knowledge of where we're using it and in the context of how we're using it, right? When we define a function literal in the context of filter, we know that it has to be a predicate, so we already know what its parameter type and return type must be. So what we just saw was we could make it call it a filter. And here, this parameter, because it has to be a predicate, we can write it without having to specify the information about what type S is, the type S parameter, or S's parameter type, and the return type of this function. All right. It turns out we can actually go even one step further, right? And if we write functions that have only a single return statement in them, right? Which is common when you're using things like filter and map, right? So this is a function that has only a single return statement in it, right? We couldn't do this if it had more than one line here, like an if statement or something like that. We can convert this function literal to what we see below, right? We don't have to write the return keyword. We don't have to surround the body of this function definition in parentheses. We can just state what is the value we want returned in this very simple shorthand syntax for a function literal. And this gets very terse and can be a little bit hard to read when you're first learning this syntax. But what I want to encourage you to remember is it's just the same as what we're seeing above. All right, so let's try this out with filter and map. All right, so with filter, what we're saying is item. If this is true, if we can actually do this, I'm going to take away this return statement, and I'm going to take away that opening curly brace, and I'm going to take away that closing curly brace, and we don't even need a closing semicolon at the end of that line, right? So I didn't even mention that, but we dropped the semicolon as well. And now look at what we're saying here. Filter input, and the test predicate that we're going to use is this function literal right here. Select only the items where the item length is greater than 4, right? And notice how nicely, once we can get past the syntactical terseness here, how nice it is to be able to specify this so succinctly, right? It almost starts reading like English when you have some understanding of the syntax that you're looking at. Filter input, where item is the length of any item is greater than 4. And so if I save this, sure enough, it's the same thing. And we could apply that same shorthand syntax to the map function, right? So the map function is saying, okay, we don't need to have the curly braces around the function literal. We don't have to have the return statement. We don't need that closing semicolon as well. And now we've reduced map. We're saying map the filtered list. And for each item, just return the first index of that item. Oops. And what we're seeing then is that's another one-liner. And we're embedding this recursive process, or we're making use of this recursive math process and just plugging in the specific logic we want applied to any individual item. So the last thing I would like you to try and pause the video and do is try calling the reduce function to take this transformed list that has U, N, C and reduce using this concatenate reducer. And notice that this concatenate reducer is just like our add reducer, but instead of working with numbers, we're working with strings. So that means we're returning a concatenated single string back as we reduce each item down. So see if you can call the reduce function. And you're going to need to be clever about how you give the first memo value. But think about if you're trying to build up a string, what is the simplest string that you would start with, the equivalent of 0 if it were a number. And try calling reduce. I would encourage you to move through the steps that we followed before. Start with reduce using this function named concatenate, then write this as a function literal. And this is another example of a function that you can write as using the shorthand syntax that we see here. So pause the video, see if you can reduce this list down to a single string value, and resume once you've done so. All right, so there's a brief question on Gradescope about this particular exercise. And now that you've got it, let's try walking through how we did it. So I'm going to reduce using the transformed list of strings, right? So we're going to keep carrying this process forward. First we filtered our list of strings. Now we're transforming them to just the letters. And finally, we're going to reduce them to a single string. The reducer we're going to use is concatenate. And the input string, what was the initial memo value here? Well, if we're trying to build up a string, the starting point for that string, right, would be just the empty string. This will be if we had no values in our transform list and we wanted to reduce the empty list to a string, it would just be a string, right? So, okay, I save this. And notice we've reduced the list of 3 string values, UNC, into a single string value. And we could convince ourselves of that reduced is a string, UNC, right? So what if we wanted to write this as a function literal? Well, I'm going to move through those same steps. So I'm going to redefine this function, memo string item string. And this is going to get a little bit ugly as I move off the screen here. String, I add my arrow, I add my curly braces. And notice I could do this and follow that up with the third parameter. And then I'm just returning memo concatenated with item, right? All right. This red underlining you might get if you have the tslint plugin installed is just complaining about how we are indenting our parameters here. And oftentimes when you write function calls that have multiple parameters that span multiple lines, the style convention is to align each parameter on its own line with one extra level of indentation. That will make that red underline go away, but that's not really important, right? It's not the formatting of this. That was just for style purposes, not for any meaningful improvement other than style and how it reads as humans, right? So I save this, and this works, right? We've defined our function literal. That's a reducer here. Well, we know that because we're using reduce, and this must be a reducer from type T string from type T string to type U string, we can drop our types here, right? TypeScript can infer these types because of the context in which we're defining this function, right? So that just got quite a bit shorter. We are now reducing our transformed list of strings, and we're taking that list of strings and reducing it to a single string by concatenating them all together. And what we just learned was this shorthand syntax, where if all we have in our function definition is a single return statement. We don't need our curly braces, we don't need our semicolon, and we don't need this return keyword, right? And so there, I've just defined a reducer that takes two string inputs, and TypeScript again is able to infer their string inputs based on how this reduce function is being used, concatenates them together, and we get UNC. If I wanted that to be CNU, I could change the way I'm reducing to concatenate the item before the built-up value, and we could see that this reducer is being applied in order from the start of the list to the end of the list. But what we really wanted here was to reduce these items one by one in the order that we came, and in this case we're computing a single string that is the acronym of our list, right? And this would have all fit on one line if I wanted it to, so I didn't need to separate these all down on one line, but you can see that once we do that, this gets to be a pretty long line. So if you do want to use the style convention of having multiple parameters, each on their own line and indented by one, this is a perfectly reasonable way of formatting it, all right? So these were the three parameters we reduced by. The point of this video was to demonstrate a syntactical improvement. We didn't gain any new capability that we didn't have before. Anywhere we are writing one of these function literals, we could have written that as a freestanding function that was defined. But the interesting thing about this is look at how quickly we were able to process this input list, narrow it down by only those values that met some criteria, transform those values in some way to focus in on where we were going with our computation. And at this point, we were trying to get to something that was the single string acronym. And then finally, we can reduce a list of values into a single value using the reduce algorithm.